This conference will now be recorded.
All right, all yours.
All right, excellent. Thanks. Okay, so I'm going to now share my screen as soon as I figure this out. Uh, oh no, I have to like grant access and all this stuff, man. Oh boy. Okay, hold on. And it's going to ask me to reboot, quit and reopen. So I have to quit and reopen,
All right,
okay?
hang on then. Maybe, Kritikesh, can you share your screen? I'm going to make you the presenter.
It's okay. I'm going to quit and reopen.
All right. Sorry, everybody. GoToMeeting is like just a pest.
Hey, we're replacing it, so um,
Yep, I'm
won't
happy to hear
won't be
that.
this way a long time.
It will be very fast.
John, welcome. I'm happy you're here.
Yeah, I'm usually busy, so I'm very happy to be here today.
Replacing it with.
Nick?
So while we are waiting for Cebu to boot up,
Yep.
this is Bill Chen. I want to mention that
Yes.
we have a outstanding session at Samacon West, and we invite everybody to come. This Samacon West session that is going to be on Wednesday, July 12th, will be focused on the supercomputer at Argonne National Lab. And so we were talking about the Intel's Ponte package and also the installation at Argonne.
Okay, you guys are able to, I've rejoined, okay? So you should be able to see this.
Yeah, hang on. I
And
need to make you the presenter. All right, please try. Bill, please keep going.
yeah, can you see my screen? It should be like the title chart.
Not yet.
Can't share your screen. We're experiencing difficulties with your video conference and unable to share your screen.
Good grief. All right, I'm going to share what you sent. Give me a second. All that means is I can't take notes. All right, that's fine.
I can let me arrange to it.
You can do
Kritikesh,
it?
yeah, can you share and I will, yeah,
Right.
and we
All
share
right.
the PPT, okay?
Okay, wait.
But I suspect, you may also have the same problem.
Let me just try once.
Oh, now that Subu Iyer is a presenter, it finally works.
Okay, all right, good. If it's happening, great, okay?
All right.
So let's see now. I'll go to full screen mode. Are you still seeing everything?
Yep.
All right, let's go. Okay, so thanks, Bapi. I mean, so I'm going to actually tell you a little bit about the work we've been doing. And actually, there are two students who have been intimately associated with this work. One is Chandra Jangam, and he now is actually was the student with whom I started all this work, and he's now at Apple. And the other is Kritikesh. Sorry for the spelling typo here, Kritikesh. Kritesh Sahu, whom I think many of you know. All right, and so we'll talk about the work we'll be doing here. So the flow of this talk is following, right? I mean, my focus actually has been in advanced packaging, and so we're advanced packaging has to do with kind of blurring the boundaries between the chip and the package, and employing heterogeneity and fine pitch interconnects at every level. So, I mean, our sort of rubric here is actually far beyond just high performance computing. I think we're looking to sort of have a much broader platform, and I'll explain a little bit of that to you. So, I'll start a little bit with the historical context, okay? and the establishment of IBM, of UCLA chips after I left IBM and joined UCLA. And a lot of the stuff that I did at IBM, where I was the director of packaging, made me realize that packaging was in a very, very archaic state, and it needed a significant amount of sort of infusion of new ideas. Okay, and at the same time, right, I got a request to write a white paper for the DARPA CHIPS program, which I did. And in that program, in that white paper, which actually became a key sort of paper for the DARPA CHIPS program, I kind of enunciated. I will wait
Hang
till
on.
the audio is done.
Somebody's not on mute, but I can't
Yeah,
find
somebody's not
your.
on mute. That's the problem.
This conference will now be recorded.
I can't. Go ahead, please, Subbu.
Sorry, Bobby.
Yeah.
I think it was caller number 3 if you want to mute.
I don't. I don't think I have the ability to mute phone callers. Oh, I can. Yes.
Okay, fantastic. So the DARPA CHIPS program, right? I wrote a white paper there, and that actually was incorporated into the DARPA call. And one of the key sort of things about the DARPA call was actually the establishment of standards. And there were sort of multiple sort of ideas on what these standards should be. One of the most famous ones, which had a lot of industrial backing at that time, was AIB, which was a protocol that had been sort of developed at Altera. And when Altera was acquired by Intel, it became a major Intel sort of thing. And so, however, as you all know, I mean, there have been many it hasn't really taken off. But the other thing we did actually was super chips, and I'll sort of explain that in greater detail today. And the idea here in this white paper was to talk about heterogeneous integration and the whole chiplet dielet concept, okay, that we kind of proposed in that white paper, which was written around 2014 or so, okay. So going forward, right, we actually are a experimental group, and so, I mean, we are not happy with just proposing things. We actually want to verify it and demonstrate it. And so we spent a lot of time, okay, trying to develop an infrastructure and develop circuits and develop chips and integration platform where we would be able to actually enable these optimized communication protocols. And one of the results of that was there were many fallouts from that program, which still continue to this day. But one of them was the Superchips hard protocol, which we'll talk about today. And going forward, right, what I want to actually talk about is actually the establishment of standards and the development of what I call translation chiplets, okay, which are, I think, going to be critically important because nobody is going to speak the same protocol, just like, the world today has millions and millions of languages. So I think the idea is how can we live, okay, with sort of uh, the existence of multiple protocols, and I think that is very, very important. And I've talked to many people. I mean, some of whom like, for example, companies like Apple and so on and so forth, who say, hey, look, we are very happy with our protocol and we're going to stay the course. We've got enough volume, we'll keep this our to ourselves, okay. And so the question then is, how do we move the needle on heterogeneous integration, chiplet dielet ecosystem, and so on and so forth. Okay, and I think this is one of the biggest challenges. And I also, with the help of BAPI and several other folks, okay, we have a program called MRHIEP, which is part of the Chips for America Act, and it is about developing a packaging roadmap, manufacturing packaging roadmap. And one key sort of aspect of that, which BAPI is leading, is actually the establishment of both mechanical standards and protocol standards. Okay, as we kind of develop this roadmap for packaging that hopefully will go into the next 10-15 years or so. All right. So this is a rough idea of what I'm talking. I'll take a little pause here and see if there are any questions. Okay.
Actually, Professor, so I know you're sharing the slide, but for some reason I cannot see anything. Though I have the slides, so maybe I'm
Wait, we're
only.
still stuck on
Uh,
slide
is
one.
everybody able to see my slides?
We're
Yes, we
stuck on
see a
slide
slide
two.
now.
Yeah,
Slide
yeah,
two.
we can see slide 2.
Oh, you're seeing the okay, hold on. That okay, now?
Now we see the outline.
Okay,
Yeah,
fantastic.
now
All
it's
right.
the presenter view, not the.
Yeah, I think you need to click swap displays.
I just swapped the displays, but obviously that is not the right one. Okay, now what do you see?
We still see slide two.
Slide two
Can you?
is the flow of the talk.
Right.
Yeah.
I think
So
that's
the
correct. I think we're seeing the right slide. I think that's just
Yeah, yeah,
all right.
if
everything is
you
correct.
Okay, yeah,
There's no
good.
problem.
Continue.
Yeah,
Thank
yeah,
you.
Yeah.
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 Let's
There's
let's
nothing to
continue.
do.
Let's
Okay.
continue.
Yeah. Okay. So let me just say a few words about UCLA Chips. I mean, it's a partnership. I mean, we have about 20 companies that are part of UCLA Chips, and we also have, a reasonable amount of funding from like the government agencies like DARPA, NIST, ONR, SEMI, which is a big part of us, especially in the flexible world, and so on and so forth, and NSF, of course, right? And our goal here is actually to develop and simplify hardware development through novel architectures, integration methods, technologies, and devices. And I always emphasize this important point that the main product of a professor at the university is the students. Okay, and so I always remind myself that our job is to develop our students, and we use sort of research and development as a way to actually develop our students so they can hit the road running, right? I mean, we all talk immensely about the problem of workforce development and so on and so forth, but this is actually a very important way. And so far, I have about 16 PhD students and roughly an equal number of master students who all do their work with theses and dissertations, and they are actually now valuable and productive members of our community. So this is actually a good thing. Okay. So what we do at UCLA Chips is we look at large scale energy efficient systems and medical engineering applications, and we further those things through advanced packaging technologies and novel compute architectures. And so we have three basic sort of technology platforms, I would call them. One is silicon as a heterogeneous fine pitch packaging platform. We call that the silicon interconnect fabric. We also have a flexible biocompatible heterogeneous integration platform we call FlexStraight, and we use that mostly for our medical applications. And then we also have a device called the CTT, the charge trap transistor, which is a high K device. And we've been basically focusing it on FDSOI technology. And it's an electrical tunable device that we use as an analog in-memory compute device. Okay. And we've actually have many applications that use that device that we've published in IDM, in ISSCC, and such like. Okay. So, but I'm not going to talk about that today. I'm not talking about flex rate. We're going to focus mostly on the SIF because that is the kind of platform that is of most interest to the folks here. So this was the a copy of the paper that I wrote for DARPA, which then was invited as an invited paper in the IEEE transactions on packaging. Okay, and this was published actually in 2016. It was written in 2014, but then we had to go through a whole bunch of stuff. And the idea here in this paper, what we had enunciated was how do we change the way we put complex systems together, okay, to reduce the time to market, to reduce the NRE cost, and actually simplify the whole process, right? And the idea was, okay, disaggregate the system into chiplets. Bare dielects are stocked, so obviously you require a dielet marketplace. A few chiplets will need to be designed, but it's a much more contained sort of proposition and will add to the dielet marketplace. An interconnect fabric is designed, dielets are assembled at a fine pitch in an onshore secure facility. And a simple communication protocol is established between the dialets. Okay, so this was sort of the enunciation of this whole heterogeneous chiplet sort of approach that today, okay, back in 2014 2015 when we had proposed this, okay, people, in fact, my colleagues in IBM basically told me that this would never happen, forget about it. I talked to people at AMD, They also didn't think it would happen, and so on and so forth. But as you can see, right, the market has developed, and today, right, it is established that this is the way to actually build things. Okay, so I want to actually point out a couple of things, right? One is that transistors are shrinking, but die sizes are increasing, right? And so back in 1993, we had the Intel Pentium CPU, 300 millimeter squared die with about 3 million transistors, zero point 0.8 micron technology. Today, right, the main sort of workhorse for everything that we're doing today in AI and ML and so on is the NVIDIA uh, uh, A100 and its follow-on, which typically have somewhere between 50 and 60 billion transistors. They have about 800, it's over 800 square millimeters in die area. And actually the latest one is actually built in the TSMC 4 Plus node. Okay, so basically, why is this happening? If you look at the die area as a function of time, right, or node, okay, you'll see that the die area has progressively been linearly and monotonically increasing, okay, for these high performance chips. And the main reason for that is, of course, there are many, but one of the reasons is actually we have more complex workloads, so we need more cores, more cache, etc., etc. But mainly because I would say monolithic chips outperform multi-die package chips. And this is because package scaling has not kept up. Okay, so what do I mean by that? If you look at the sort of scaling of silicon, right, it's shown in the blue curve on the left. Okay, use on a log scale, you'll see, that's the more famous Moore's law. But if you look at package scaling, right, IBM introduced, and you can look at any metric on package scaling, right? You can look at bump pitch, you can look at trace pitch, you can look at everything. And basically, right, if you come to this, you come to the realization, and that's on the right hand side on a linear scale. When IBM introduced bumps, for example, C4 bumps in 67, they were about 400 microns pitch. Until about like 2010-ish or so, we were sitting around 200 micron pitch, right? And today, right, if you look at the commercial world, mostly these pitches, if they're solder based, right, are stuck at the best around 30 to 40 microns, 30 to 50 microns pitch, right? Now, if you go to like solder-less sort of bonding, either metal to metal thermal compression bonding that we do at UCLA, or hybrid bonding, that is another very popular way of doing it, but it has some limitations. We won't go into it. But you find that you can actually shrink that pitch and go down. And today at UCLA, for example, we are routinely doing 10 micron pitch. We build prototypes for companies and so on and so forth with TCB at this 10 micron pitch. And going forward, right, we think we can actually get down to about 5 to 7 micron pitch with this technology. And then after that, right, we would have to go from mechanically aligned die to die or die to wafer approaches to lithographically aligned. Okay, and that is something that we're also working on, but it's beyond the scope of this talk, so I won't talk any more about it, right? The other thing about that people talk about, and there's a lot of buzz, about heterogeneous integration. Now, heterogeneous integration is nothing new, right? If you take any PC board, it's heterogeneous. Okay, the key thing that is different, okay, in today's heterogeneous integration is the ability to replace, a few board channels with a large number of board channels. Okay, and this ability, okay, which is driven mainly by the developments in advanced packaging, allows us to go from this very highly serialized interface or very fast interfaces, even if it's not serialized, okay, to a very, very parallel interface. And this actually, as we all understand, right, gets to lower power, lower latency, and higher bandwidths, and simpler IOs, and much more useful chip area. And this is a very important point, because if you look at these very high-speed IOs, okay, they tend to occupy a large amount of area on the chip. Okay, so and we'll come back to this point a little later. So what do we mean by all this? More channels on the package, which means finer bump pitch and pillar chip. And when I say fine, what do I mean? I mean you want to approach, okay, the on-chip via pitches, right? Remember what we said, that we want to blur the distinction between chip and package, right? So what we would like to do is get down to the on-chip via pitches at the highest level, which is typically, submicron. All right. Finer trace pitch. Again, it's the same principle. We want to approach the on-chip wiring pitches. Okay. And this is also very important to do. And the last thing we want to do from a technology perspective is short inter-die distances. So if you look at different IPs on a chip, they're butting each other, right? But we can't do that in packaging because we have to mechanically align the chips. And so, but we believe we can get down to micron separation between dies. So I call this whole part of the advanced packaging thing scale down. And scale down can be viewed as sort of quote unquote a Moore's law for packaging, right? What we want in our roadmap is that to progress just like we had the silicon roadmap, where we religiously kind of decrease the minimum feature by zero point 0.7 every 2 to 3 years. We need to have a roadmap, and this is the whole idea of the MRHIEP. We need to actually go off and deliver a roadmap where we continuously reduce the size of these important features on the package. The other thing we need to do is actually have a lot more intimately connected silicon. Okay, so this, if you look at the way we do things today, even if you look at, say, the NVIDIA A100, okay, you need like 100,000 of those units, okay, to actually do a sort of a large language model, for example, right? And so what we really need to do, the other big thing we want to do is we want to have significantly more intimately connected silicon. And I call this thing the scale out sort of imperative of advanced packaging. So basically, when we talk about advanced packaging, okay, we talk about two things: scale down and scale out. Okay, and this is really, really important, and I think this is the way we're going to actually pick up the slack that silicon scaling
我现在在
has.
上班呐。
Hello.
Oh, sorry.
Yeah. Okay.
Sorry.
Accidental crosstalk.
Okay. Yeah, dude, this is another problem when you have intimately connected silicon, right? Okay, so yeah, I think these are the two key messages I like to give people. Okay, when we talk about advanced packaging, right? Scale down and scale out. This is very important, and everything we do, okay, has to kind of keep this in mind. This is where we want to go. Okay, so in 2019, we put a whole bunch of these ideas together based on sort of experimental work that we had done and theoretical calculations and so on. And we came up with sort of some guidelines on where would be a good starting point. Okay, and so the optimal connection pitch, and this is the bond pitch. Okay, this is if think of it as a bump pitch, the pillar pitch, whatever. We came to the conclusion that it has to be somewhere between 2 and 10 microns. So today, right, so we started at 10 microns, but our goal is eventually to get to a 2 micron pitch, which is like a 1 micron kind of connection, right, area. And the other big thing that we came to the conclusion of, and I won't go into the gory details here, but you can read it in this paper, is that there's an optimal dielet size. And this optimal dielet size is where the yields are higher, the handling is easier, the testing is simpler. And that is between 1 square millimeter and 100 square millimeters. And so the dielet ecosystem needs to comprehend this, and we need to be able to come up with dielets where we have commonly used IP that occur together and kind of fabricate these dielets and have them in stock. And how do these dielets connect to each other? They have to connect at reasonably fine pitch so that they look monolithic from the outside world. Okay, and this is really the whole idea of how we started and why we are doing what we're doing. So now, if you look at in the same paper, right? We also the title of that paper actually was for AI systems, right? And we said like the only thing that and this predated the sort of work that is happening in large language models and so on and so forth. Where we said, look, if we really, we have two big problems, right? Everybody is aware of the memory bandwidth and memory wall problem, right? That is one problem. But there's actually another bigger problem, and that is underutilization of the memory and stagnant memory, okay? And this last two problems have to actually do with the fact that even if we increase bandwidth, okay, we are unable to actually access all the resources that are available. And so as a result, right, even though the data exists somewhere in the system, processors cannot get to it. And so what we proposed at that time is the so-called checkerboard architecture, where, and I like to use the name of that movie, right? Everything, everywhere, all at once. So the idea here is processors and data are everywhere and all at once. So in other words, the memory is uniform and equally accessible. So today, right, near memory can be accessed, say, in about tens of nanoseconds, but farther away memory, okay, will require thousands of nanoseconds to be accessed, right? Now, if we are able to actually build a wafer scale system, for example, like this, let's say, have 70,000 square millimeters of silicon, where we have stacked 3D memory and stacked 3D processors and so on and so forth, okay, and connect them intimately like this, both vertically as well as horizontally, what we can end up with is a really, really uniformly accessible memory where every bit is accessible from every processor within like about 50 to 70 nanoseconds. Okay, and that is really the goal that we are trying to do. So if you look at today's sort of large language models and so on, right? Even with NVIDIA's like hotcake selling processors, right? We really run out. A single thing runs out with we will run out of like space and things like that, including with parallelism when we reach about say 1 billion parameters, right? And so today we are already, we have to concatenate many systems, because today's sort of things use like 17 billion parameters, and we are probably going to go to multiple hundreds of billions of parameters to actually make this happen. So the key things that are required are computation, more uniform shared memory, and a very, very high degree of connectivity. And then the other very important thing is power, right? And this, I was in a discussion with Scott DeBeer from Micron, who they're actually a big memory supplier to all these things, and they said, look, 63% of the power in these LLM sort of workloads, okay, is for data transfer. In other words, more than half the power is just moving data from one place to another. Okay, and so obviously, this is where I think the big fruit is, right? And so that's really what we're trying to do. So towards that end, right? I think we actually published in 2017 this paper in ECTC. Okay, and it talked about the superchips integration scheme and protocol. Okay, and in fact, this was in my opinion, and if I look at like the things that you guys have been doing on Bo, I mean, it's exactly the same thing. But as I was telling Bapi yesterday, we published this in 2017, and actually the paper itself was submitted in 2016, right? And I think the point I'm trying to make is like, we share some of the same ideas here if you look at it, except that we are pushing this to much higher levels of integration and much lower powers, okay, using a combination of technology and sort of protocols, right? And this work that Shiva did actually received the Best Student Paper Award at the ECTC in 2017. And also, just in this ECTC, this work and the other work that's associated with it, Shiva actually got the Outstanding Young Engineer Award from the IEEE EPS in not 2019, in 2023, sorry, partially for this work. So this has been in the packaging community, right? This has been pretty well accepted, okay? But and so my goal actually today is to make you folks be aware of it. So at the open in ODSA, so that you guys can see what we've been doing, okay? So I'm going to let Kritikesh take this chart. You want to take this chart, Kritikesh? Are you there, Kritikesh?
Yeah, yeah. Can you wait? My computer is acting up.
Okay, forget it then. Okay. So basically, while you get your computer, so what are the key things here, right? The key things that we developed to make this all happen was direct metal to metal bonding. That is a critical thing because solder based bumping will reach a sort of wall around say 30 to 50 microns. Okay, and that's why today's interposers, for example, are stuck around 30 to 40 microns, right? The fine pitch interconnects, so this bumping has to be at less than 10 microns, so we get more data links, and obviously we get higher bandwidth, right? We eliminate, actually the other thing that we eliminate is die level packaging, and the other very important thing, okay, is our assembly method. Okay, we reduce inter-die spacing, okay, of less than 100 microns, and this is very important, right? Because the whole idea here is to actually reduce the, when we try to build the system, that is checkerboard system that I talked about earlier, okay, what we want to be able to do is make the wires between the chips look like wires on the chip. And that means, okay, that we want to run these at frequencies where they do not look like transmission lines, okay, but they look like simple RC elements, right? And single pole thing. So that eliminates the need for termination and so on and so forth, and reduces channel loss, right? And of course, the latency between the chips because of the short space is reduced, so we can actually get in our protocols, right, less than 30 picoseconds of latency across from one chip to another, right? So if you do all these things, you reduce the driver complexity, you reduce its size, you eliminate SerDes, and actually significantly reduce IO power. And so we basically, and this is exactly what you guys have said in the Go architecture, right? You can replace these very complex SerDes and even sort of things like DDR and QDR and so on and so forth with much simpler sort of inverter, cascaded inverter type drivers, okay, that are adequate for many of the things we do. And this actually overlay shows, where we are, so we can actually get a lot more channels, okay, by reducing pitch. So it's very important that protocols have to be tied to the technology, and we know where the technology is going, right? If you look at sort of Vcache and things like that AMD's announced, they're at 10 micron pitch, okay, and this is going to go down. There was a paper at this year's ECTC where they talked about like a 0.5 micron pitch, but they didn't show any results because I don't think they had any, okay. But the net of it is that pitches are going to decrease, right? So you have to kind of comprehend that. So are you there again, Kritikesh? You want to take this, or should I continue?
Yeah, I can probably, yeah, I can see these charts.
Okay, very
So
good.
I guess, yeah. So yeah, so right now, I think in this chart we're basically showing our capabilities using the SIF, and you can see there are about like 100 dies or something bonded to one corner of a silicon wafer, and these are all bonded at 10 micron pitch. And our approach to bonding is basically thermal compression bonding. So you have a direct copper to copper integration, and by removing any solder, we can actually do this at 10 micron pitch, and we can further reduce the bonding pitch to 7 microns. So by using equipments which have better alignment capabilities. So we have maybe we are not exactly going into the details of the reliability results here,
Okay,
but
yeah,
we have
it's okay. You don't have to do that. I think just the
correct.
demonstration is good enough. And
Mhm.
yeah, so what is super chips? I mean, we've already talked about it. It's a very simple thing. So this is the actual schematic of the circuit, and basically, okay, we're able to get these kind of numbers, 30 picoseconds, and this is experimental numbers, and energy per bit of 0.03 picojoules per bit, data bandwidth of up to 8 terabits per second per millimeter, and so on and so forth, right? And then this is from those papers that were published in 2007. 17. Okay, this shows that we actually are able to make these things in experimentally, and we were able to measure actually the characteristics of the super chips protocol. Okay, and basically measure things like insertion loss for almost a half a millimeter, greater than a half a millimeter links, all the way up to 30 gigahertz. And basically, what we're seeing is exactly what we thought. I mean, this thing looks like a single RC, single pole behavior, right? So going forward, Shiva also did a lot of other measurements, for example, crosstalk and near end crosstalk, far end crosstalk, and so on and so forth. I'll leave all these charts with you,
Yep.
but basically, right?
Can
I
can
mean,
can I ask a question?
mhm.
What are the ESD structures for this?
Yeah. So one of the key things we did here is we did not use ESD. Okay, and we took special precautions, okay, so that we could actually do this without ESD. Okay, now in later work we have actually added ESD, and but we've added a very specialized, low capacitance ESD, and we'll talk about that a little later. Now our assembly technique,
I'm
okay.
sorry. And what process technology is this?
Pardon?
22 nanometer
What
at the moment.
what's that?
Yeah,
What is?
22
I'm sorry.
nanometers.
One
22
guy,
Okay.
please.
nanometers.
Let me ask him the question. What's the
Yeah.
question?
What process technology? What process technology?
Yeah, so
And
we
you said
actually
yeah.
get
Okay.
our chips from commercial foundries. I'll show you in a second. Why don't you hold that question and I'll come back to it, okay?
I'm sorry. I just was able to talk here. Last thing, and this is on a substrate or an interposer. What's the
This is on the silicon interconnect fabric. So think of it as a PC board, but made of silicon.
so
Okay?
it's a silicon interposer.
It's not an interposer. It's the thing. It's the platform for a wafer scale system. But you can use it on an interposer if you want. It's completely agnostic. But we use the silicon interconnect fabric. Okay?
So the fabric is active. Is that what you're saying? The underlying
Fabric is
fabric is
passive.
actually active.
The fabric is passive. It's just a bunch of wires. I mean, a collection of wires. I'll show you. One sec. Okay, hold on for a sec. And so this is, we also had a bunch of macros where we did like obviously continuity checks, latency characterization, and then measured bit error rates and so on and so forth. So this is work that Shiva did for his PhD dissertation. Okay, and this shows a schematic of what he actually built. And this was built both, and we also built some functional macros. I'll show you that in a second. Okay, that use the super chips macro. So this is an example of what we have here. Okay, and basically we did this. Test vehicles were fabricated both by TSMC. I mean, we designed them and fabricated them in TSMC 16FF and also in GF22FDX. Okay, there were two different dies that were actually taped out. And what we do actually is we pull these wafers at the last copper level, all right, and then passivate them. So basically we design pads. These pads are typically like 5 to 7 microns in dimension. Okay, and these pads are then passivated with silicon nitride. Okay, and then they're shipped to us. So what we do, okay, at UCLA is we strip the silicon nitride, we do a quick clean, and then we submit them to the thermal compression process on the silicon interconnect fabric that we actually built at UCLA. Okay, so basically the two chips, multiple chips, can only communicate through the silicon interconnect fabric. There's no other way for them to communicate. So you guys are clear with that? Okay. So what you see here actually in this picture here is the silicon interconnect fabric. Okay, and we have 4 dies here. These are functional dies. Okay, and they have channels. I think these are 16 lane channels. Okay, using the super chips protocol, and they can communicate like this. In the one direction they are synchronous, in the other direction they're asynchronous, so we can actually test both modes of communication, right? And we also had like the 22FDX die, which we used to measure a lot of the intrinsic characteristics of the superchip macro. And then we assembled four of these TSMC 16FF dies on the silicon interconnect fabric, okay? And then this was then mounted on a PC board. The only reason we had to do that was because we had to kind of connect it to a FPGA board, okay, and we did that through wire bonds, but everything is contained within the silicon interconnect fabric, okay? So it's just to stream in the testing patterns and so on and so forth. So what you see here are the different dies, and the distance between the dies is about 55 microns, okay, and so on. So this is kind of the structure that we had, okay. So all this is real. Okay, we do this routinely, and we're actually building now much bigger wafer scale systems that are based on this idea.
So I'm
Uh,
sorry. So how is this different than a silicon interposer? I'm trying to understand that.
This does not need anything else. We deliver power, everything to it. I mean, we don't need an interposer is something that comes between. There are no TSVs in this.
Okay.
Okay.
So you're saying it replaces both the silicon interposer and the organic substrate into one
Exactly.
piece of silicon.
Yeah.
And then this is all, well, don't you, and the only way you get off of here though is with wire bond, because you don't have any TSVs to come down to a
No,
bulb.
actually, we have actually some high speed connectors. We can add to this. We can add fiber optic connectors and so on and so forth. So this is beyond the scope of what I was planning to talk to today.
All right.
But if
If
you're
I, so
interested,
if I need 3,000 balls, this is not a.
pardon,
I said if I need 3,000 balls, this is not a.
3,000 balls. What do you mean?
My devices have 3,000 balls on the bottom of the BGA part package.
I can give you millions and millions of balls.
Between me and the PCB board.
Yeah, I mean, I can. I mean, you don't need the PC board. Why do you need the PCB board?
There's a system around me. I mean, I build high-end
Yeah, so
FPGAs.
you can connect
My
this.
customers want to connect.
Yeah, so you connect it with connectors, okay, and you and those will have a lot more connections. If you want to do it with balls, you can do it, right? That's but it's kind of a waste of it's like the whole idea here is to actually build
Yeah,
large systems that are
tell you
self-contained.
what, why don't you send me your email address in
Yeah,
the
yeah, yeah.
chat, and
I'll be happy
we'll talk.
to. I think I don't understand your question, so I'll follow.
I'll connect you guys offline.
Yeah, yeah, great, thanks.
Thank you,
Yeah, no,
Bobby.
I do want to actually follow up with you. What's your name again?
Nick.
It's
Nick
Nick
Iliadis.
Iliadis.
Okay, great, great. So yeah, I'll look for your email. Yeah.
Hang on, I'll do it
Okay.
right now.
Yeah. So Kritikesh, you want to kind of take this chart?
So, so on 2022, this summer results we presented in 2022 ECTC. So basically, these are the macros. Shiva graduated, and basically, I took this setup and I did a lot of detailed measurements with VDD scaling and both for latency as well as for energy. So previously, professor had talked about all the macros that he had taped out to measure the latency of the links as well as the energy of the links. And here you can see the latency. So at a nominal VDD of 0.8 volts, we actually have a latency of the link less than 20 picoseconds. Um, and also we are able to do data transfer up to like 2.5 Gbps. This was limited by the programmable oscillator which we had on the chip. So we're able to get a bandwidth of 1.2 terabits per second per millimeter on a two-layer SIF. We did a lot of bit error rate measurements for more than 100 hours, getting a bit error rate of less than 10 to the minus 15. Also, we measured the energy per bit for these links, which is about 0.028 picojoule per bit, and less than like 0.03 picojoule per bit. So, so the only thing is, I think that professor talked about, we actually did not have any ESD on these links. We basically relied on our process and technology to make sure that our bonding is ESD free. We were using all precautions that are necessary while we do all this bonding and all that. But we were able to get all these really good numbers.
Yeah, so we did not have any ESD events. I think we should emphasize that. Yeah. Okay. So going forward, right, we actually published a functional macro, okay, and this is a what we call a universal DSP processor that was actually designed in 16FF, okay, and this is expandable in 2 dimensions, and so we actually built this. This is the first functional demonstration of a chip assembly at 10 micron pitch. I mean, this was done, presented in 2021, I believe, right? In or 22, actually,
22 in
in
ISS, yeah.
an ISSCC, and a more complete paper was published in JSSCC in 2023. Okay, so all and basically this is actually a real application of the all the technologies we talked about here. So we've actually looked at sort of comparing our super chips with other sort of SerDes and other things like Info, LipinCon, and so on and so forth. And basically, I mean, this combination of technology and simple IOs allows you actually to get significant improvement in figure of merit, right? And this figure of merit that we are talking about here, okay, actually includes things that there was a DARPA figure of merit, which was bandwidth per die-edge divided by energy per bit. But what we have done actually is we've actually included in it, okay, with another figure of merit actually, which we have not sent here. But basically, this includes things like the amount of area that is used on the chip and bit error rate and length of the link that you're trying to drive and so on and so forth, right? And
Hey,
I think,
Professor, we're down to about 5 minutes.
yeah, so let's do this. So right now, actually, we're building a wafer scale system, okay, with multiple dies. This is a prototypical large scale learning machine that we're building, and so this is now we've got this consists of multiple dialets, each a chip tiles, and each tile consists of 8 dialets that are intimately connected, memory die and a processor die. And now we're actually scaling this up to a full wafer system. The other thing we sort of want to emphasize here is that signaling standards, IOs occupy a fair amount of silicon area, they burn a lot of power, et cetera, and they also tend to be very proprietary and resist standardization. This is a very important sort of realization. Okay, and so one of the things that Kritikesh is doing right now, he's developing with the help of Synopsys, okay, a translator chiplet, okay, and I think this is a very important development because this can take our goal eventually is to have any incoming protocol translated to super chips, connect multiple dies in the super chips protocol, and then translate it back to an outgoing protocol which may be different from the incoming protocol, right? So this concept of the translator chiplet is actually a very important one, and Kritikesh is actually trying to prototype such this concept, right? And Kritikesh, very quickly, can you go through this chart?
Yeah, so as a demonstration, basically we'll be having two of these ships. We call them Anuvad for translation. Essentially, we have our SIF, we have the superchips links, and we put two of these ships. So as the first iteration, we are just going for PCIe to superchips and back to PCIe. So the way it will be done is first you on the number one, basically we first build the system on the SIF. We do some partial testing to make sure the assembly is functioning as intended, and then you take the system and basically flip it and put it on a PC board, basically to again give these 10 gig connections through SMA connectors, which still there is in a very effective way of putting them directly on the silicon interconnect fabric. But But to just give these signals at high speed, that's why we put it on the PCB. We do the conversion here. We verify that we can do the protocol translation, and then basically back convert it back to another high-speed protocol and basically compare the error. So that's the general idea for this test vehicle.
Yeah. So this thing is being taped out as we speak, okay, in GF22 FDX. So going forward, so as advanced packaging blurs the line between chip and package, we would like super chips to be an operational hard protocol basis for all near-end communication. We're recommending that in the roadmap that I am developing with under the auspices of NIST with SEMI as well. And so, what we are looking at as a silicon interconnect fabric, scaled interposers, such with TCB or hybrid bonding, 3D stacks, and so on and so forth. So low energy, low latency, near neighbor hardware interface should be agnostic to soft protocols, which can ride on top of them. Superchips takes advantage of advanced packaging using, say, the silicon interconnect fabric, but not necessarily. It can also be used on interposers and overcomes complex I/O designs. And basically, it leverages fine pitch integration, tight dielet to dielet spacing, and short channel lengths. So under the name Anuada, we're trying to actually tape out some translator chips. We think we'll be able to integrate a large number of other protocols as well, if necessary, and including proprietary protocols with our members. So wafer or die to substrate bonding using hybrid or thermal compression bonding is going to be the common mode of packaging at fine pitch. Okay, this is where the industry is going. Okay, and for high performance sort of systems, and our goal is to prototype IOs for the same and solve the challenges that arise, and that's really what we're focused on. So I'll stop here, and I thank you for your attention. Yeah, and I'll look forward to questions, including by email.
All right. Maybe we can bring Kritikesh back for questions since we're at 9 a.m. We're likely to lose everybody. Um, thank you. Oh, Zeng's saying that. Thank you. Anybody else with any questions, any thoughts?
No, it's a great talk. I really appreciated it.
Oh,
Thank you.
thanks. Yeah. Yeah, so
Thank
I
you.
mean, look, I think this is really, I mean, where we're going with advanced packaging, right? And so I think we really have to kind of, and what I really want to do with you folks is actually socialize what we're doing here and see how we can kind of make all this happen in the industry. Okay.
All right. On that bright note, happy 4th, everyone.
Yeah. Happy
Thanks
Fourth,
again.
everybody. Yes. Okay.